Dear colleagues, thank you very much to attend us. So welcome in Moscow State University. It's our first school in the field of ecology. So hopeful that it will be a very fruitful time in Moscow State University. So in the first lecture from the professor and member of the Russian Academy of Science, Natalia Tarasova. So welcome. Thank you very much.
Good morning, dear colleagues. First of all, I apologize for not managing to arrange a good weather for you. But you know that nature has no bad weather. Any weather is good and there is sense. So I'll start my lecture with the dedication to Professor Pietro Tundo. I do not know if any of you had a chance to participate in summer school in green chemistry in Venice, but Professor Tunde was the founder of green chemistry on this planet. In late 80s, last century, together with Professor Paul Anastas, he started this theory, first of all, and then he organized a subsection in Union of Pure and Applied Chemistry. You know that this is an international organization that is responsible for the development of chemistry and chemical industry on this globe. And then he was one of the founders of the Interdivisional Committee in Green Chemistry for Sustainable Development in IUPAC. Fortunately, he passed not long ago, but we who worked with him are trying to explain his role to the younger generation. And if you have a chance, please read his papers. He worked a lot on green chemistry, especially on chlorine-free chemistry. So this year is very important for sustainable development and for sciences in general, because this is the International Year of Basic Sciences for Sustainable Development. I do not know how many of you knew about this fact. May I ask those who are aware to raise hands? Okay. International Year of Basic Sciences for Sustainable Development is not widely known to the scientific audience on this planet, but you are lucky because next year, the decade of the United Nations Basic Sciences for Development will start. So I hope that in 10 years, you will hear something. While 1 year was not enough, I hope that 10 years will be enough, and you will become the leaders of this movement. And I would like to show you some quotations from the opening speech of this year. The opening ceremony took place in Paris, in the UNESCO headquarters. And you know UNESCO is United Nations Cultural and Educational Organization. And what is the most important here in this quotation is that basic sciences have an important contribution to make to the implementation of the program on sustainable development on the planet. And they provide the basic sciences, the essential means to meet crucial challenges such as universal access to food, energy, health coverage, and communication technologies. And it helps people to live on a healthy planet and to reduce negative impacts such as depletion of the ozone layer, climate change, depletion of natural resources, extinction of living species. And it's also known that contributions of basic sciences are not well appreciated. They are not nonetheless the basis of major technology that will help and stimulate innovations. And this international year gave a unique opportunity to convince all stakeholders that though a basic understanding of nature, actions taken place will be more effective. I started my speech with this quotation because, first of all, I'm a member of the steering committee, so I feel some responsibility to let as much people as possible know about this decade. And then I'm a teacher, and the teacher is one of the most important professions on the globe. I'll explain you why a bit later. Dmitry Mendeleev, and you can see here the latest version of his periodic table, which has element number 118. And maybe you know that Professor Oganisyan is alive. He is in good health. He still works. And at the same time, he is here forever in the history of the humankind. So Dmitry Mendeleev, who was a scientist and educator, also wrote about the role of basic sciences. He said in his book, Selected Writings on the Periodic Law, that the function of science is to discover the existence of general reign of order in nature and to find the causes governing this order. And this refers in equal measures to the relations of man, social and political, and to the entire universe as a whole. I hope we'll excuse Dmitry Ivanovich for using man. I hope ladies will excuse him. At that time, gender problem was not as important as now. And in my speech, I'll deal also with relations of human, social, and political, and the relations of humans with the universe. The most concentrated role of basic sciences in the life of the planet might be found if we analyze the Sustainable Development Goals. I hope this is known to everyone, or not. Could I also please ask you to raise your hands, because I should be aware if someone doesn't know. Please raise your hands who have ever heard about Sustainable Development Goals. Thank you. At least now, those who didn't hear will hear. Okay. So in all of these Sustainable Development Goals, we can find a place for basic sciences. And as I represent chemistry, I should say that in 7 goals, chemistry is playing a vital role. What is chemistry? This is a definition which is very popular in Russian scientific community. Chemistry is the music of nature, which, while playing with a limited number of elements, 118 at the moment, creates the infinite beauty of the universe. So that's what chemistry is. And we all are participating in the symphony. And if we look at the tree of life, because our life is chemistry, it's chemical and biochemical processes, you will see which place Homo sapiens occupies on this tree of life. So this is image very popular in the family of ecologists, biologists, which shows that if we take the position that all the living creatures on this planet originated from the same initial system of molecules, you will see that in this variety of species, humans are here, and you will soon see who are our closest neighbors. They are mice and a very small creature. It lives in Latin America in swamps. So this is a tree of life. This is biodiversity. We are here, one of examples of biodiversity, but we are different from others. And this difference is the fact that we possess reason. So, tree of life, everyone is alike, but there is one type of living organisms that is very specific on the planet, and it differs from the others by the fact that human beings possess reason. I do not know if you had a chance to think about this quality of human beings, and if any one of you has his or her own definition of reason. But one of definitions is a capability of foreseeing. What that means? You can step back, you can look at what is going on, you can analyze, and then foresee what will happen. And this powerful action helped human beings to create science, to create education, because science and education, this is exceptional quality of Homo sapiens. And here are different definitions of chemistry, science about nature, science about matter, science about the properties of different compounds, and even the way two individuals relate to each other. You know, there is chemistry of love. It's very popular now in psychological circles, at least in our country. Some people investigate how chemically you can make someone fall in love with you. I think it's not good, but nevertheless, this is one of the definitions of chemistry. And chemistry helped, alongside with other basic sciences, human beings to become one of the most powerful forms of life on the planet. Academician Vladimir Vernadsky, this is an outstanding scientist who is not well known outside Russia, but I think that history will put him on his proper place in the humankind history. He wrote about human beings and about the noosphere, the sphere of reason I have just mentioned. And he wrote this paper in 1944. And you know that 1944, this is the period of the Second World War, very dangerous period for the humankind. And nevertheless, he analyzed the future and he thought that global reason, the reason of all human beings on the planet, will help to create a new state of the environment, which he called noosphere. And so this is a quotation: the impact of humans is becoming comparable to the most powerful geological forces. When I think how could I illustrate this quotation, I usually show this Iguazu Falls. Are there anyone from South America? If anyone had the chance to see this beautiful, powerful structure created by nature. And when we, the members of AUPAC, we had a conference in Brazil and we visited the Iguazu Falls, we were standing here. I was trying to understand what Vernadsky wrote. Impact of humans is comparable to the most powerful geological forces. So imagine myself, though I'm not very weak, and iguazu falls. Difficult to compare. But nevertheless, this is a fact, and this is confirmed by science. And this capability of thinking made it so that the humans do not obey the normal laws of distribution of number of species according to the unit mass of a species. So this is a plot of number of species on the planet, and this is the unit mass of individual species. Bacteria are somewhere here, and you know that the number of bacteria is very high, the most abundant type of living organisms. This is mice. Mice, our neighbor, you remember, on the tree of life, etc., etc., etc. The bigger the unit mass is, the smaller is the number of species on the planet of this type. And you understand why, because this is the ecological niche, food that is needed, space that is needed, etc., etc. So if we were like others, and I respect all forms of life, we were somewhere here, and the total number of humans on the planet was about 100,000. This is a fact. But we are not 100,000. We are about 8 billion, practically. And there are some other examples of deviation from this simple plot. Our friends, cats and dogs, may I call them friends? Does any one of you have a cat or a dog? No. Do you consider these living creatures your friends? Of course. And sorry to say, our food. So friends and food, they also do not obey this simple law. And this is one of the demonstrations of this quotation from Vladimir Vernadsky, that humans are becoming a very powerful force comparable to other geological forces. Why are we here? Why we do not obey the simple law and live simple life in harmony with nature? Because we have reason. And it helps us to transfer knowledge from generation to generation and not to repeat the mistakes of the past. But it's not correct. Now we are repeating the mistakes of the past. And due to this capability, due to transfer of knowledge, we came to a new state of the environment, which was named Anthropocene. And Rockstrom, with colleagues, about 15 years ago, they started this work. In 2009, they made a publication in Nature, and the statement was like this: the planet's environment has been unusually stable for the past 10,000 years. This period of stability has seen human civilizations arise, develop, and thrive. Such stability may now be under threat. Since the Industrial Revolution, a new era has arisen in which human actions have become the main driver of global environmental change. Rockstrom never heard about Vernadsky. I asked him. And you see, the same idea came in quite a different part of the world. Humans are becoming the most powerful geological force. And this could see human activities push the Earth system outside the stable environmental state of the Holocene, with consequences that are detrimental or even catastrophic for large parts of the world. Here are the symptoms of this trend, and I'm sure all of you, being the environmentalists or ecologists, or people interested in the future of the Earth know about this. Of course, the exponential growth of the population, though it is not discussed widely, because it's a very delicate question, in fact. The exponential growth of population is a very delicate question, and in different cultures, it is treated in different ways. And so for politicians, it's quite convenient not to touch this problem. It's much more interesting to touch the problem of the CO2 emissions, species extinctions, boundaries for nitrogen and phosphorus cycle that has been overcome, etc., etc. I have only one question for you. When this trend, this exponential trend from the straight line, and all of you as natural scientists, you know that when the parameter is small, the exponential curve is just a straight line. And then all of a sudden, it becomes a real exponential curve. Do you know when it happened? If it was still a straight line, we would have now about 4 billion people, quite a comfortable planet with highly developed science, education, a lot of resources, no problem. It's interesting, but this curve became really exponential in 1940s. It was the Second World War. People were killing each other quite effectively. And nevertheless, the curve became real exponential. Why? Science, antibiotics, a drastic drop in mortality, especially women mortality, expected life period is growing up, etc., etc. And just one comment. And now, with these antibiotics, we've got into another problem. You know this problem. Antibiotics everywhere, bacteria became resistant, more and more antibiotics, better and better bacteria resist. Again, exponential growth, but it's another problem. But in fact, it is again the same problem. It is a problem of human reason and of capability to foresee the consequences and take care of them before the activity has started. And of course, you know that all these trends, all these problems are interrelated. It's very complicated net. And to find the only solution, I'm not sure it's possible, in fact. Nevertheless, science was trying to make predictions. Again, the question for the audience, how many of you have looked through this famous book, The Limits to Growth? This is a publication of the Club of Rome. It was done in 1972. And in 1972, more than 50 years ago, this group of young scientists, some of them were younger than even people in this audience, they were 25, 27. They created the first global model. And this model showed that in 20s of the 21st century, humanity will get into problems. This is non-renewable resources. And this is the timeline. When the work was done, the depletion of non-renewable resources was about 10%. No reason to worry, 10%. Etc., etc. Population was not high. food per capita good, food industrial output good, pollution low. That's where we are now. When curves became something with maximum, it means that here the situation might become critical. You understand what I say? This is a kind of a crisis. And that's why I recommend you to read this work, because we are now here in this period. And if you look through the scientific paper, you will understand why. We have now crisis in industrial output, we have crisis with renewable, non-renewable resources, we have pollution that is growing, we have a population under the threat of decline in 20-25 years. And it is called the so-called standard run. It is the behavior as usual. The same work showed that there might be quite other future for the humankind, education, new mentality, new life paradigm, not to consume, not to be the society of consumers, to be the society of learners, to be on good relations with everyone, etc., etc. And in this case, the predicament was that the situation could be stabilized, the population stabilized, etc., etc. But no one heard, listened to them, and now we have what we have. And this is, again, the quotation. And you can read it, and again, I'll read it for you. The past societies have reacted when they understood that their own activities were causing deterioration, environmental change by controlling or modifying the offending activities. It's clear. In fact, Sustainable Development Goals and the whole story with this movement in the United Nations is this is the attempt to do this. The scientific evidence has now become overwhelming that human activities are influencing the environment in ways that threaten the well-being and continued development of the human society. You are specialists. I do not need to understand this, to explain this to you. If humanity is to learn from history and to limit these threats, the time has come for stronger control of the human activities that are changing the fundamental conditions for life on Earth. And in fact, every sustainable development goal is oriented towards this. Every SDG is for this. And the whole concept of sustainable development is the result of this analysis. And you know the definition, meeting the needs of the present without compromising the ability of future generations to meet their own needs. Brilliant definition. And living within the Earth's carrying capacity and understanding the limits of the natural resources and limits of the possibility for the Earth to absorb waste and regenerate them. And of course, reducing poverty. And here with this poverty, and you understand that this is a mentality, this is a lifestyle, etc., etc., etc. It was mentioned in 1976 in another report of the Club of Rome that well before reaching the physical limits of our planet, severe social disturbances will occur due to the huge economic gap between poor and rich nations. 1976. I do not comment. You can think it over later. One of the problems. No one will argue that reducing poverty is the most important thing. But it means increasing consumption. increasing in natural resource use, and in the generation of residues and pollution. So what shall we do? Should we freeze the state as it was? Should we do something else? And Herman Daly, who passed not long ago, he wrote, one of the famous economists of our world, that the global economy is now so large that society can no longer safely pretend it operates within a limitless ecosystem. It means that the human activities are comparable with the Earth as a planet, as a physical object. And growth is widely thought to be the panacea for all major economic ills of the world. And here, I draw your attention to the difference between the words growth and development. And from my point of view, it's very important. Growth is a larger quantity of objects with the same quality. 1 car, 10 cars, 100 cars, million cars, exponential growth. And development, it's object with new qualities. And to reach sustainable development, we do not need growth. We need development. And this is a very important issue which should be explained to the younger generation, especially. Not long ago, I had a discussion with one of the decision makers. And when I asked him, it was he, while he speaks about growth, while the planet is limited, Earth is limited, and infinite growth is not possible on a limited planet, but development is possible. I got no good response from my point of view. And the final quotation I give to you, it is from Mahatma Gandhi. The world has sufficient resources for the needs of all, but not for the greed of all. And once again, the problem is humans. It's not the environment, the quality of resources, it is the problem of humans. That's why I mentioned to you that the role of a teacher who transfers knowledge in a non-genetic way from generation to generation is becoming very important. And that's why in Russia, this year is the year of teacher. We have a special year of teachers. And what else I would like to point out, we transfer knowledge in non-genetic way. Genetic heritage is efficient. It was proved by the whole history of the development of the planet. But non-genetic transfer from generation to generation through schools, through education, through mass media, through internet, etc., it's much more efficient than for other living creatures. And you remember this curve. That's why we are not 500,000. That's why we are billions. And this is the example of the model run, which I mentioned to you. It was possible to stabilize population, to stabilize food per capita, industrial output, even to stabilize the pollution and not to deplete all the non-renewable resources. If these measures I mentioned were undertaken in 1970s, last century, but no one listened to this predicament. It's funny that last year, when it was 50th anniversary of the publication of the Limits to Growth, 222, and it was published in 1972. Nature, the most respectable journal, published an article, and they wrote, Dennis Meadows and his team were correct. We are sorry to blame him and his team for being badly educated 50 years ago, because 50 years ago it was written that they do not know economy, they do not know this, they do not know that, and all this has nothing to do with reality. So, excuse, but it's too late. And again, we're now living beyond the limits. And here are several symptoms of overshoot mentioned by Dennis Meadows in his publications. And you can read, and you will not object. Rising levels of pollution. This is interesting. Growing demands for capital resources and labor by military and industry to secure, process, and defense sources. Again, I do not comment, just read what's investment in human resources, education, shelter, healthcare, postponed in order to provide immediate consumption and security demands. It's all over the world. Rising debt, eroding goals for health and environment, growing instability in natural ecosystems. In Moscow, +7 in November. It's a little bit strange. And finally, growing gap between rich and poor, between the powerful and the weak. Again, it's 50 years ago. 50 years ago. And you will say, how can you prove that this predicament was correct? As a natural scientists, we would like to have some experiments. But to make experiments on humans is not allowed. Nevertheless, there are data, and this is the non-renewable resources. For example, this is from Growing Within Limits. It was published 15 years ago, practically. And the lines are the lines from the computer models. This is the crisis model, and this is sustainable model. So blue crisis, green sustainable, and the dots are statistics. So population, non-renewable resources, industrial output. I'm sorry, this is population and pollution. What else do we need? This is the experimental proof of the fact that the model was more or less correct. And currently, we need 1.7 planets to meet the needs of the living generation. These dates, they show when we start to consume resources from the coming generation. We consumed everything Earth could give us for our generation, and now are taking from the coming generation. And this year, it was July 24th, as far as I remember. So starting from July 24th, we consume the resources for the next generation. Would anyone of you guess what helped to move this date closer to January 1st? Because January 1st is very good. We had a year for us. Now we start the next year without consuming the resources from the next generation. Epidemia. When we had this pandemic, immediately the date moved to September. Can you imagine? Instead of July, as this year, we moved to the middle of September. People consumed less, people had another type of life, etc., etc. So again, this is an interesting fact. And this is another demonstration of exponential growth forever for all non-renewable resources. For some of them, it's still a linear, straight line, but soon it will become like this. And especially rare earths and other metals which humans need to produce electronics, it's a very hot issue now. And again, this is the conclusion from the publication of Rockstrom I mentioned earlier. So human activities push the Earth system outside the stable environmental state of the Holocene. with consequences that are detrimental or even catastrophic for large parts of the world. And Rockström published, and his group published a very interesting paper, and they introduced a new term, planetary boundaries. Again, if any of you have heard about the theory, planetary boundaries, but it's quite logic. Earth is limited, humanity is growing, so science should look for boundaries. And if we overpass the boundary, catastrophe will come as Meadows predicted. Very simple. So they have selected quite, I could tell you the story, but I will not know. They selected a certain number of boundaries, which they considered to be the most vital for the life on the planet. Among them, climate change, this is a boundary. We have now more than 400 ppm, as you know. Ozone layer depletion, the only example when humans united and made a right decision. So it's more or less okay now. Acidification of the ocean, freshwater use, agricultural land use, and each of you can imagine Latin America, for example, Brasilia, and agricultural land which is eating the virgin forests. So biogeochemical cycles, this is the load of nitrogen per year, this is the load of phosphorus per year, vital biogenic elements, loss of biodiversity. And here are two boundaries which are not defined. Atmospheric aerosol loading, TBD, to be defined, and chemical pollution, TBD. Why no figures? Very complicated problems. Scientists did not take the responsibility to predict. So to be defined. Be very careful here. They say to chemists, maybe we are already there. Maybe we are already on the boundary. And this is the demonstration of how life looks like now, biodiversity loss, nitrogen cycle, phosphorus is reaching the boundary, climate change, ozone layer depletion, more or less okay, and the other are here. But life is even more complicated because we are social creatures, and not only physical boundaries of the planet limit the development of the humankind. There are social boundaries. Every one of you would like his or her voice to be heard. Resilience is important. Education is needed. Income is needed. Water, food, health, gender equality. You remember I mentioned at time of Mendeleev, it was not an issue. Now it's an issue, etc., etc. And so for sustainable development, there is a thin layer between physical boundaries of the planet and social boundaries of humankind. And we are somehow to fit in there. And it is, again, sustainable development goals. This is an example of phosphorus pollution, though everyone thinks phosphorus is very useful. Nevertheless, it can destroy the environment completely. It's in Florida. And here comes another ethical issue. Archibald Hill is a Nobel Prize winner in physiology, and he wrote, if ethical principles deny our right to do evil in order that good will come, it's clear. We should not do evil in order that good will come. Are we justified in doing good when a foreseeable consequence is evil? We did good. We produced more food, but the consequence And again, this is a reason, this is a capability to foresee what will happen. As I mentioned, sustainable development goals are important. I'll accelerate, it's my time from straight line to go to exponential because I limited in time. And this is a new modification of planetary boundaries. And instead of chemical pollution, novel entities were added. This is genetically modified food, so, but still undefined. Everything is undefined still. Functional diversity of the biosphere was added because it's very important and it's not well understood by fundamental science, and et cetera, et cetera. And phosphorus has become worse, the situation with phosphorus. And still there are a lot of topics to investigate. So chemical pollution and basic cells in chemistry will grow up considerably by the year 2030. It's a fact. It demonstrates the rapid growth even among other branches of industry. Meanwhile, chemical compounds, though we all are chemistry, and chemistry is our life and our future, they possess risks, and they pose risks. Even sporting goods and wood and construction, et cetera, and some of them have high risk. For example, household chemicals, furniture have low risk. By the way, batteries last year has been moved here to the high risk. And when reflecting on this, Dennis Meadows asked to the journalists, they asked, do the technologies exist that can help save the humanity? And that's what he wrote. In fact, the technologies required to dramatically reduce global problems already exist, but the motivation to use them for that purpose does not. There are technologies, there is no motivation. Again, this is a problem of humans. It's not a problem of environment or something else. Without changes in the institutions and motivation governing the development and use of new tools, the problems will persist irrespective of the technologies we develop. That's what a very wise man, he is now 80, said. And you remember he started when he was 27. So the role of transferring the knowledge to the younger generation is very important. And I mentioned to you the role of teacher. And this is very interesting results of a survey. Respondents from the UK asked the question, what is their association with chemistry? Science, elements, research laboratory, periodic table, reactions, et cetera. Look here. This is a chemistry teacher which showed them the wonders of the world. And that's why we have this year of teacher in Russia in 2023. So green chemistry is chemistry that does not destroy the environment and that helps to resolve all the problems of the humankind. You will further have more detailed lectures on this theme. My goal was to show you that in this limited situation, something was to be born, and this green chemistry was the result of the reflections of Professor Pietro Tunda, his colleagues, and many others on the world. Here are the principles of green chemistry. There are 12. They're very simple. And any normal scientist follows them if you are well educated chemist, you always follow principles of green chemistry. For example, pollution prevention, reduce derivatives, use of renewable resources, etc., etc. It's very well developed field of science now. And the role of professional society is to distribute information about green or sustainable chemistry. It's another interesting issue. In some Western countries, green was associated with opposition. Greens in Germany, for example, that's why they use term sustainable chemistry to avoid political problems. So, but in fact, sustainable chemistry and green chemistry, they are quite alike. And one more quotation from Nobel Prize winner Roald Hoffman: organic chemists, molecules are molecules, chemists make new ones, transform old ones. Still others in the economic chain sell them, and we all want them and use them. Each of us has a role in the use and misuse of chemicals. I see chemists as actors in a classical tragedy. We are sentenced by our nature to create. There is no way to avoid investigating what is in or around us. If you don't find that molecule, someone else will. And at the same time, I believe that scientists have absolute responsibility of thinking about the uses of their creations, even the abuses by others. And they must do everything possible to bring those dangers and abuses before the public. If not I, then who? It is this duty that makes them actors in a tragedy and not comic heroes on the pedestal. It is this responsibility to humanity that makes them human. That's why green chemistry. There is no green physics yet. Biology is green always, but there is green economy. But they were not the first. First, chemists came because we are not comics. We are heroes. It's very interesting experience that is taking place now, preparation of GO7 report for the United Nations, Global Environmental Outlook number 7. I am part of this activity, and this is the address which was published in the beginning of this work. And it is stated now that we have a triple planetary crisis, and that policies are not addressing the systems in the right way, and that scientists should help them to change their minds. And I'm coming back to nature. Do you know this animal? It's widely spread in Eurasia. And this creature needed shelter and food. And global climate change came. The shelter was frozen in the permafrost. Then again, global climate change, the permafrost melted, and the Russian scientists found this hole, copper hole in the permafrost. And this is the result of the experiment. This flower is 32,000 years old. So Hopfer, without any reason, helped us living now to see the beauty of the world 32,000 years ago. What will we bring to the future generations? And here I again quote Professor Meadows: no matter what happens over the next decades, at each moment there is always an opportunity to do many different things. Some of them will make the situation better, and some of them will make it worse. And it's ethically satisfying and probably even effective in some way to try and find the things that will make things better. I don't know what's coming. If I were to conclude with any sort of simplistic recommendations, I guess it would be to build up your social networks. Use them as a source of new ideas, support, reinforcement, and satisfaction. And that's what I wish you during this School of Ecologists. Thank you for your attention.
Thank you very much for this awesome presentation. Do you have any questions? Yes.
Thank you, Natalia Pavlovna, for a brilliant presentation, but your speech was very pessimistic. And as I see, we must stop the existing economics and create new one to solve all these problems. Can you give us some sort of optimism for the future?
Dear Ekaterina Sergeyevna, I cannot agree with you. I was trying to smile during all my lecture, first of all. Then I was trying to show that there are brilliant people who reflect, who think, and who try to find the solutions. And I'm not pessimistic. When I'm a teacher, I'm always optimistic. I do not tell you what I feel when I am alone, but as a teacher, I'm optimistic. Otherwise, there is no reason to live on this planet.
Yeah. Any more questions?
But by the way, Ekaterina Sergeyevna knows a lot about green chemistry, and she collaborated many years with Pietro Tunder, and there were mutual publications. So if you would like to know more about him and about green chemistry and IUPAC, please approach Ekaterina Sergeyevna Lokteva, professor of chemistry department of Moscow State University.
Yeah, thank you. One question from me, maybe we don't have an answer now, but so you showed that this exponential growth of population, of course, we all aware of it, and all the problems that are coming with the number of population. So what the scientists thinking about solution of this problem? Should we stop the growth of the population, or should we develop, I don't know what, maybe I see many quotations here that the greed is the problem, maybe not the number of population, but the greed of the government, of the peoples who want more and more, I don't know, energy, resources, etc. Maybe, so what scientists are thinking about the solution?
You remember that we have social limits, boundaries, and physical boundaries. We cannot do anything with physical boundaries, but we do have possibility to change social boundaries. So what is needed? Feedback is needed to decision makers. They should understand that their electoral mass feels that the situation is critical, that something should be done. So first, communication to decision makers from my point of view. Second, communication to the younger generation, because when they are deep in online life, they something forget about the neighbors. And it's very dangerous, and all over the world, people discuss this. We are not the cyber creatures. We are Homo sapiens sapiens. And so it's a good combination, but again, no one could foresee the results of the development of computer science 50 years ago. And what is the most important, never stop thinking. Never stop. A person who has his or her own position will always find an escape from the situation.
Thank you. One more.
Okay, thank you for the nice presentation. You already answered my second question. What can the youth of 21st century do? Because you gave us the solutions from the past generations, the causes of problem we've caused now, and you already said not to stop thinking. That's the solution. Okay, so my other question is, what are the research and innovation of green chemistry right now?
So I'll start with the end, if you do not mind. Green chemistry is the most important instrument to achieve sustainable development goals, because in any case, you will need chemical compounds to construct buildings, to feed people, to grow up children, etc., etc. But these results of chemists' activity should not destroy the environment. So green chemistry is an instrument that helps to create good without doing evil. And there are a lot of directions in green chemistry. We have schools of green chemistry here, and Professor Tunda had schools in Africa, in Rwanda. The year before, he had schools in Asia. Everywhere we organize schools. This is my first answer. And then you see, we should think about resilience, adaptation and resilience. If I'm a pessimist for 1 minute, then we are already past this limit. And then we should prepare for unexpected events, for catastrophes. And in this case, science should take care of resilient solutions and of adaptation. And by the way, if you look through the governmental programs in your countries, please do, you will find their positions dealing with resilience and adaptation. How to replace population from the seashore in countries if the sea level will go up. How to change permafrost for something else. In my country, we have a problem of permafrost. It melts, and big towns, they just being destroyed. Who could foresee that it will melt? It's another thing. And the epidemics of different types, new biological entities, I mentioned it. So there is a lot of things to do for science, but still I'm optimistic. I'm optimistic. And by the way, very special attention is now paid to African countries, because you remember this position about poor, about the economic growth. There shouldn't be growth, there should be development. And the mistakes of the past shouldn't be repeated.
Okay, it's just a sum up. Is green chemistry also the optimistic
Yes.
revolution to?
Yes.
Are you optimistic about this?
Exactly.
And this is the progressive way forward to go. Okay,
Yeah, yeah.
thank you.
And one short question: what do you think? Can we reduce consumption to reach this 1st January of consumption from future generations? And maybe when?
You can never get back to the past, first of all. So in coming 10 years, I do not think it's possible. But nevertheless, attempts should be done. And what is the most important is to change the mentality, way of thinking. And I would like to tell you that from the time of Neanderthals, ancient people, the volume of human brain did not change. We have the same volume of brain in our head. Before, scientists thought that volume of brain is the most important, then brain should grow. And you remember fantastic novels, One Big Brain. It just grows. And now we speak about development. So we should develop our brains and networks. And Vernadsky wrote that this is not the volume of a single unit brain that is important. The global volume of knowledge is important, and we should know how to share it. Did I answer your question to some extent?
To some extent, yeah.
Okay.
Thank you very much. Let's thank Professor Taras Vadim. And thank you. And now
I do not know what is your tradition do. I could leave my presentation, and those who are
Yes.
interested could then copy it.
if it is
But
possible,
please
yes.
refer to me, because as Dennis Meadows says, sometimes they interpret your words in the wrong way. Then please refer to me.
Thank you. So, and now we will start the opening ceremony.
Начинаем. So, good morning, dear colleagues, ladies and gentlemen. On behalf of the Moscow State University, as a scientific head of the chemistry department of Lomonosov Moscow State University and Russian Academy of Science, as a vice president responsible for chemistry and biology, I would like to welcome you on International School on Ecology. So, welcome to Moscow University, welcome to Moscow. I hope you'll spend this time in productive discussions between yourself and discussing the materials that will be presented during the lectures and seminars. And I hope it would be really important for you to have new knowledge of different environmental practices, control of the environment, and many, many other things. So unfortunately, the weather is not very good for going outside for sightseeing, but this is good for lecturing. Actually, there will be nothing that would be interrupting your ability to visit lectures and seminars here. But anyway, I think there is some social program that is also included into the timetable of the summer school. I would like to tell you that this summer school, that this International School on Ecology, this is one of the schools, series of schools that we have here in Moscow State University in different aspects of waste management, decommissioning, and nuclear medicine and related topics. So in terms of ecology, this is the first international school. I hope it would not be the last one. And the important thing that all these series of international schools, they are conducted in Moscow State University in collaboration and under cooperation with Rosatom. That is a state corporation for nuclear energy in Russia. And I would like to give the floor for welcome remarks to my very good friend, Andrei Lebedev, who is the director. I would like to read it, not to miss anything. Director of the Direction on State Programs and in the field of ecology and environment of State Corporation Rosatom. So, Andrei Vladimirovich, the floor is yours.
Добрый день, дорогие друзья, уважаемые коллеги. Я рад вас сегодня приветствовать на запуске этого уникального проекта. Сегодня первый раз собирается международная школа по экологии.
Good morning, dear friends, ladies and gentlemen. I'm very glad to welcome you here at this start in life of this first time unique international project, International School on Ecology.
Безусловно, это стало возможным благодаря длительному взаимодействию в предыдущие годы со стороны госкорпорации Росатом, Российской академии наук, а также Московского государственного университета имени Ломоносова, в частности, химического факультета, на котором мы сейчас с вами находимся.
This event is due to long-term cooperation and interaction between the state corporation Rosatom and our scientific institution, Lomonosov State University, and the Russian Academy of Science, and in particular, the Department of Chemistry and Radiochemistry.
Конечно, я бы хотел поблагодарить за партнерское, конструктивное взаимодействие Степана Калмыкова. Благодаря работе совместной мы сегодня умеем уже целый ряд уникальных решений, которые могли бы быть использованы на благо государства и для того, чтобы делать экологию в наших странах более безопасной.
So, and first of all, I would like to thank Mr. Stepan Kalmykov, and due to our cooperation, we managed to find a number of interesting solutions that benefit our state and make our environment more safe.
Конечно, все знают госкорпорацию Росатом в первую очередь благодаря атомной энергетике, это и АЭС, Это и атомные станции малой мощности, сегодня уже как наводного, так и наземного исполнения, и также целому комплексу вопросов, связанных с обращением с радиоактивными отходами, с чем сегодня госкорпорация Росатом успешно справляется.
So people know Rosatom Corporation due to many, of course, facilities related to nuclear energy, and in particular waste management, and which we have a few projects which we successfully proceed.
Безусловно, тот научный потенциал, те производственные возможности и те компетенции, которые были наработаны в атомной области, позволяют также активно сегодня развивать и другие направления, реализовывать широкий спектр зеленых проектов.
So due to our competencies and good experience in nuclear development, we have an opportunity now to develop other projects related to green energy.
Конечно, сегодня вопросы экологии, вопросы устойчивого развития, вопросы безопасного обращения с использованием современных технологий с промышленными отходами тоже стоят на одном из передних планов и являются такими приоритетными с точки зрения тех акцентов, которые мы должны с вами делать.
And today our environment, and in particular waste treatment, is the priority. It's one of the priorities for all of the actions related in this field.
Поэтому сегодня мы в течение государства совместно взаимодействуем над тем, чтобы более эффективно уже в рамках экономики замкнутого цикла обращаться с опасными промышленными отходами, которые образуют наши предприятия.
So according to our instruction from the government, now we are working to proceed with the projects in the economy of closed cycle to make hazardous waste treatment safer.
Также мы имеем большое количество объектов так называемого накопленного экологического вреда. Это то наследие, с которым мы, безусловно, сегодня должны разобраться, должны привести огромные территории в безопасное состояние, чтобы они не несли угрозу жизни и здоровью людей, и, соответственно, экосистемы привести, создать условия, чтобы они восстановились.
So in Russia, now we have a number of so-called accumulated damage facilities. These are large areas which we need to somehow find solution, how to make them safer, how to abandon them safely, or and decide what kind of further life we should think of for these territories.
Я очень рад лица госкорпорации приветствовать уникальный преподавательский профессорский состав, в том числе из других стран, наших друзей, потому что большое количество решений, которые, как я уже сказал, мы вырабатываем при совместной работе, при взаимодействии с Московским государственным университетом, с Российской академией наук, могут быть референтными и могут быть использованы в том числе на других таких объектах и в интересах наших друзей-партнеров из дружественных стран.
So we are very glad to welcome our experts from different countries who came here together, because we believe that our mutual experience will be valuable for each other and we'll be able to share it with each other.
Желаю всем интересной, плодотворной работы. Надеюсь, что Международная школа по экологии станет традиционной, и мы на системной основе будем иметь возможность взаимодействовать, и это обязательно принесет свои плоды и результаты.
So I want to welcome you once again, and I hope that this International School on Ecology will be a traditional event. It will be a regular event where we'll be able to benefit each other in the most possible way. Thank you very much, and have a fruitful cooperation and work. Thank you.
My great pleasure to give the floor to the representative of the office of, we call it Rosprirotnadzor, that is a state agency responsible for environmental protection and ecology, Dmitry Viktorovich Fedotkin, who is responsible for Moscow and Kaluga region, that is the nearest to Moscow. Dmitry Viktorovich.
Dear friends, I'm really very glad to see you, but sorry for my bad English, I will speak Russian. Я приветствую вас от лица Федеральной службы по надзору в сфере природопользования, Росприроднадзора и руководителя службы Родионовой Светланы Геннадьевны.
I want to thank you very much for this warm welcome today, and on behalf of Svetlana Rodionova, the head of Rosprirotnadzor, which stands for Russian Nature Control Authority, I want to welcome you all here.
Приветствует и поддерживает создание и начало работы первой экологической школы, созданной при ведущем российском учебном заведении Московского государственного университета при поддержке Росатома и Федерального экологического оператора.
Our agency warmly welcomes the International School on Ecology, which was organized with the support of Russian Academy of Science and Moscow Lomonosov University.
Очень рады, что на базе МГУ молодые люди из разных стран, изучат передовой российский международный опыт ликвидации накопленного вреда, ознакомиться с передовыми экологическими практиками.
We are very glad that people from many countries will share the experience here and find new solutions, learn new knowledge related to waste treatment.
Помимо надзора, основной своей функции, помимо государственного экологического надзора и оказания государственных услуг природопользователям, служба также реализует различные экологические проекты, среди которых выделяется экологическое время «Экология – дело каждого».
So in addition to control and nature management, we also have a special award. Our agency has this award, which is called Environment is a matter important to everyone.
Надеемся, что участники школы либо самостоятельно, либо всей школы участвуют в этом конкурсе, очередной 4-й этап, который стартовал буквально месяц назад.
And so we hope that participants of this school, either together or maybe separately, will participate in this competition because the final 4th stage has just started.
В Московском регионе, в Калуге, за который отвечает наше управление, тоже реализуются передовые экологические проекты в области экологического транспорта, в области очистки стоков, сбросов и выбросов, а также ликвидации накопленного вреда и другие экологические проекты, с которыми мы будем также рады вас познакомить.
So in Moscow region and also in Kaluga region, which is close to Moscow, we have a number of projects related to environmental transportation, waste treatment, water treatment, wastewater treatment, and we will be glad to make you acquainted with our projects.
Мы приглашаем всех на работу в Росприроднадзор.
We invite everyone to work at our agency, Rosprirotnadzor.
So, dear friends, dear colleagues, I announce the International School on Ecology open. So let's start.
So, dear colleagues, we continue our school, and now I think all of you prepared some presentation. So let's start from the presentation, from yours. Please, who will be the first? Okay.
Сидеть сейчас, пока не...
Okay.
Или...
Оля.
Спасибо.
Людмила, please come to me. Переводим. No. Right now. Are you ready?
Yes.
Yeah.
Yes, of course. Добрый день, уважаемые коллеги, участники нашей школы.
Hello, dear colleagues, again.
Еще раз добрый день, уважаемые участники нашей международной школы. Я очень рада вас видеть. Заочно познакомились с кадром. Я надеюсь, наша школа будет очень интересной, для вас полезной. Мои коллеги уже вам, в принципе, дали небольшую вводную.
I want to welcome once again our guests today. In correspondence, before the start of the school, we already met each of you and communicated with each of you. Hope you will find this school useful.
В рамках нашей школы мы с вами проведем технический тур. Мы посмотрим один из объектов, который мы полигон Красный Бор в Ленинградской области.
So within the frames of this school, we will have a number of technical tours. In particular, we will visit St. Petersburg region with a dump that we are going to dispose in the nearest future. And you will have an opportunity to see how we are going to do that.
Также вы послушаете различные лекции, очень известных представителей науки, части экологического и мониторинга, радиоактивного контроля, экологических проблем. Также наши сотрудники федерального экологического оператора расскажут вам более подробно о наших проектах, которые мы реализуем. И было бы очень интересно, чтобы это было не только лекция, да, а от вас обязательно была обратная связь, потому что именно эту деятельность мы хотели бы транслировать в ваши страны и находить взаимодействие в этом направлении.
Also, you will be able to listen to a number of lectures from our very famous experts who specialized in waste treatment and other related spheres. And what is important for us is that we're waiting for some feedback to you to understand, let's say, your perception of these lectures, because we want to implement our ideas and our experience in our friendly countries and your countries. That's why the feedback from your side will be very appreciated.
Соответственно, у вас будут еще практические занятия. И после посещения полигона Красный Бор нам бы хотелось провести некую интерактивную игру, где мы с вами фотографировали на предмет, как мы можем реализовывать такие проекты.
Also, you will have some practical studies, practical seminars and lectures, and we are going to make the so-called interactive game, maybe some simulation after you visit the facility in Krasny Bor in St. Petersburg region, to understand, maybe to make a brainstorm and then get some understanding of the new ideas which will arrive.
Также мы надеемся, что прослушав курс наших лекций, в следующем году кто-то из вас изъявит желание и может быть уже подавателем для следующих участников нашей школы.
And hopefully, after the number of the lectures that you will listen to, maybe some of you, by the next year, will already have ideas and give your own lectures and become a lecturer, a professor in our school and prepare your own program. Thank you very much again. I'm very glad to see you all here. And I congratulate all of us with the start of work of our first school on ecology.
Yeah, so dear colleagues, we have finished our welcome speech. Maybe currently we have a little break, about 10 minutes. So, and after that, we will start the presentation, all of you. Thank you.
methods, how to in waste management and so on, and of course meet new people from other universities and change with them our experience and gain new one. Thank you all for attention. We're a team from Belarus.
Rashid, please.
Thank you. It's open last time. Okay. Hello, everyone. My name is Mohammad Rashid Sardar. I study in National Research Nuclear University, Moscow Engineering Physics Institute. It's located in Kashirskaya. So it's in Moscow. So the thing is that, okay, the next slide. Oh my goodness. Thank you very much. So I was basically, I'm a citizen of Bangladesh, my home country. So in my country recently, there is a faculty nuclear engineering department is opened. It was opened in 2014 with the master's degree and then BSc because of the need of building nuclear power plant. As you know, Bangladesh had a cooperation with Russian government, mainly with Rosatom, the state corporation, to build its first nuclear power plant in Rupur. So that it can contribute the electricity demand to fulfill the electricity demand, the ongoing crisis in Bangladesh for its development, sustaining development, sustainable. So I was a student in Dhaka University. After 3 months, I got the chance to study in Russia in my university, the one that I'm right now in. So after this studying in the university, I participated in many different programs, like in the University Student of the Year program and also internship program from Rosatom service. My life goal is supposed to be a professional engineer, a nuclear engineer in any nuclear facilities, and also to contribute to the science society to build much better algorithms or something like new to predict the temperature of the fuel rods or heat capabilities or any neutronic behavior of the reactor of the active zone or the active zone, I may say. So I also participated in the internship program in JSC Atomistro Export, which is also organization of the Rosatom. And it was great to participate in those programs provided by Rosatom as it may create more opportunities for young generation, for young people. So, as I said, a nuclear engineer, also a professional, to be a professional in the job is my goal, future goal, and also a high value person, so that I can face any kind of difficulties in life, and I can pursue my dream to be strong and be confident in whatever I will be doing. So that's my goal. Thank you very much for the attention.
Thank you very much.
I'm really glad to greet Rashid back in Moscow because, you know, he participated this summer in international summer schools on radiochemistry, and it would be interesting to mention that he came to us, he joined us for the summer school right after he was working on the erection of the nuclear power plant in Bangladesh. So I'm really, really happy that he is a part of our team at the moment. Thank you, sir. Rashid, for coming.
Hello. Nice to see you. Yeah, thank you.
Hello, good morning. My name is Mohammed Mashroof. I am from Pakistan. My field of experience is waste management, but I basically chemical engineer from University of the Punjab in 2001, late decade of days. My experience is a radioactive waste management, not industrial waste, domestic waste, hazardous waste. My total experience in radioactive waste management, and Pakistan has 7 to 8 nuclear power plants. We have research reactors, and we have other nuclear activities, and there is generation of waste is almost tons of in volume and tons of it. So we are involved in the safe and secure waste treatment, waste collection, and waste disposal packages. After that, we are planning for safe disposal of radioactive waste. We are planning in this time, we have 2 repositories for planning, and I think it will be operational in 2027. And my interest of field here is how to save our environment, how to save our ecosystem, how to save our fauna effects of nuclear waste. And here my interest is different studies regarding waste management, their effects for million of years, their effects of 100 of years, their effect of 300 years. Low short-lived radionuclides and long-lived radionuclides. And I also share my expertise, my knowledge with my colleagues, with Rosaitom. And especially I thank to Rosaitom for giving me this opportunity to share my knowledge and to gain a lot of knowledge from your side. Thank you very much.
Thank you very much. So I have no presentation, I think. No, yeah, it's true. So maybe we can take to you the microphone. Yeah, who will be next? Maybe you. Okay.
Thanks. Hello, everyone. My name is Ekaterina Kazimierskaya. I'm from Belarusian State Technological University at the Department of Industrial Ecology. I am a graduate student at BSTU, and the theme of my PhD work is obtaining of magnetic sorbents from ion-containing production waste, and I would like learning more important information about radioactive waste, because for my country, the obtaining nuclear energy is a new way for obtaining energy for our country, and this is important theme of future of our future. Thank you.
Yeah, colleagues, please. Who will be the next?
Okay, we will take a list. Okay.
Hello, everyone. I'm Shahrabanu Mahmudova. I came from Antalya, Turkey. I am a doctoral student at Akdeniz University in Environmental Engineering Department. And I have a biology teaching experience at Baku, and I graduated also biology at bachelor degree. Then I graduated ecology at also at master degree, and now I'm continued my education at Tunisian University, and my research areas microplastic solutions on soil ecosystem. I have several. Firstly, I would like to thank you to give me this opportunity to participate this school, and I hope it will be beneficial school, and I think we will get new knowledge, new experience, and that's all. Thank you for thank you for I forget for attention.
Good afternoon, ladies and gentlemen. I want to thank you for being part of you. My name is Olabode Jones Ajimijere. I'm in Nigeria. I studied at People Friendship University. My BSc on civil engineer, and I did my master in business and industrial management, and also continue in PhD in innovation management. In this case, I'm so interested to join this program because of my expectation of learning and information. That's actually why I came to join this program. And actually, I'm a politician in my country and representing my country here in Russia as the chairman of Russia and Belarus. So I also have a director on a new company on Quora company, which is also concerning to ecologies and management issues. So those are the area why I joined this program. I'm so glad to be part of you, and I believe I will continue learning so that I can go higher and also assist my country in the area of management and ecology management in all areas. Thank you so much for listening.
Who's next? Hey.
Good morning, everybody. First of all, I would like to thank the organizers who helped us to come here to get this experience. I am associate professor of chemistry in Bahar Dar University in Ethiopia, and also associate member of a new program on nuclear engineering. As we also started cooperation with the Russian government to start to build a national nuclear power plant and a national nuclear science and technology center. And in that context, I am also a national experts group for nuclear science and technology. And I have been also in Moscow from into 2022 schools on radiochemistry. My expectation and goals in this conference or in this school is to get further knowledge on waste management in general, particularly in radio waste management. And finally, I wish you all a very nice stay. Thank you.
Hello, my name is Marina Pilipenko. I am from Belarus. I have worked in the system of the Ministry of Natural Resources and Environmental Protection of the Republic of Belarus for almost 20 years in Brest Regional Committee. Most of the time my work was connected with the issues on waste management. I also dealt with emission into the atmospheric air and protection of water resources. I participate in the realization of many international projects. including those of waste. I have studied in Bavaria and China and attended training seminars in a number of European countries. I have qualifications of Master of Biological Sciences and researcher in the field of technical sciences. In the near future, I plan to defend my scientific work. Currently, I am an expert in the field of research efficient and cleaner production. Thank you. Have a good day and productive work.
Hello, everyone. Ojawale. Okay. Ojawale Oladokun is my name. I am a civil engineer from my bachelor's, and currently I'm studying nuclear power engineering in the field of thermal hydraulics at Tom State Polytechnic University. I have been working with Nigeria Atomic Energy for the past 7 years in the areas of nuclear fuel cycle, radioactive waste management, and nuclear safety and security. I joined this program because Nigeria is about to enter into a whole lot of contract about building its nuclear power plant, and the experience of a civil engineer is needed. And also, we trying to make a part in the ecology where a large and vast land is needed, where most of the animals and everything that contains the environment needs to be studied, and a lot of challenges because there were several programs where we could not reach a compromise on what species of animals, what species of waters and all trees and forests should be preserved. So I tried to apply for this program to see how best I can contribute my own quota to my country's energy projects. Also, my goals and expectation for this program is to be a knowledge base for the coming generation in my country. And I'm a nuclear technology promoter. I love to teach, and I also want to, in the nearest future, impart more knowledge on the coming generation about the environment and existence of our ecosystem for a better generation. Thank you.
Good day, colleagues. Good day, colleagues. My name is Hondibov. I'm from Kazakhstan, Atyrau region. I'm health, safety, and environmental manager of Nasar Solutions company. Our company engaged in disposal and recycling of hazardous and non-hazardous waste and wastewater. And you know, in my country, in Kazakhstan, and I think in other countries, we have a problem with disposal of waste. For example, plastic, batteries, radioactive wastes. And for example, in our country, the main method of chemical waste disposal is incineration. And now we are in search of a solution for chemical waste recycling or processing with secondary use of this waste. And I hope to exchange experience and gain new knowledge in waste management and waste disposal methods, maybe. And I just want to say thank you for let me to take part in this educational program. And nice to meet you. Thank you.
Don't hesitate to speak for yourself. Not everybody has introduced themselves, so ladies first, I believe.
Hello, my name is Alisa Koskova, and Kyrgyzstan is my homeland. This is the place where I grew up and learned some life. And I always knew that I wanted to do science, and my first option was physics. After 3 years of hard studying physics, I decided due to some circumstances, I decided to take up chemistry, and I didn't regret my choice at all. Now I'm studying at Mendeleev University of Chemical Technology on Faculty of Biotechnology and Environmental Problems. I like to learn the world. I like to study the world from the point of view of science, and I really glad this opportunity to International School of Ecology to study something new for myself, and it's really important for my to my country, because we have a lot of gold companies, and it is a problem that they use a lot of gold, and the element is gone, and in future it will be a great problem, like economical problem and environmental problem, and that's all. So I really like to learn something here that will help me to make my country better. So thank you for your attention.
Good afternoon. My name is Melkam Anjulu. I am from Ethiopia. Actually, Ethiopia and Russia has a long time history, starting from Alexander Pushkin, who is the father of Russian language. And we have many international relations in politics, in religious, and the other one. This Moscow is great city. I was here for 5 years. I studied my master's in National Research Nuclear University in nuclear physics and technology. Especially, I did my master thesis in recycling of nuclear waste materials. Those materials used for MOX fuel or another's. Now I am studying second year PhD student in the same university, National Research Nuclear University. I am trying to do something recycling of nuclear fuel, especially we can find from waste nuclear materials or spent nuclear fuel, proctactinium and neodymium. Actually, we don't have any proctactinium still now, but with my supervisor and the other colleagues, we are dealing to find that one. And from this International School on Ecology courses, I find something that is like Professor Natalia says that it's about green chemistry. Maybe we can find something about green physics or maybe green atom. And then next, maybe when we go to St. Petersburg, there also we will see something. It will helpful for me to have my dissertation. So I think we will enjoy this school and have a nice time. Thank you.
Good afternoon, everyone. My name is Oля Volynets. I'm from Belarus, Brest. So it's cool to see here people from Belarusian universities. Currently, I'm studying at Mendeleev University of Chemical Technologies of Russia at the Faculty of Biotechnology and Ecology. Also, I'm mastering additional education, translation of scientific and technical literature. So I want to help my country to solve problems with radiochemistry with sustainable development. I get great pleasure from studying microbiology. So I'm glad to be here among open-minded people. Thank you so much.
Okay, good afternoon. My name is Wogan, and first of all, I'm glad to be here. And about my educational history, I finished a bachelor's degree in Ethiopia. It was mechanical engineering. Then I came here and joined St. Petersburg Polytechnic University, hoping to help my country in energy sector. And I studied thermal power plant engineering. After that, I just joined again PhD program in the same field in the Energy Institute. And parallelly, I'm working in a waste recycling company in St. Petersburg. So the company is more focused on recycling waste, which are related with oil, plastic as well. So I have some experience, and I want to gain some of others colleagues have been working on other sector of waste. So I'm glad to see you here, and I'm happy. Thank you.
Good day, everyone. My name is Anel Raparkul. I'm from Kazakhstan. Currently, I'm a first-year student of master's program at Mendeleev University of Chemical Technology. But what's interesting, from the bachelor's degree, I'm a marine engineer. I crossed the Atlantic Ocean on the sailing vessel, but due to some circumstances, I couldn't continue to work like a seafarer, and then I changed my specialization to process engineer. Now I want to work in the plant. In my hometown, we have the big company which deals with the process of mineral fertilizers and phosphates. It's also interesting that chemistry is totally new for me, and from this course I expect to discuss the chemistry from the recycle sides, and from the university I expected to discuss the chemistry from the theory. Thank you for your attention.
Hello, my name is Evgeny Shinkarev. I am a foreign student of Mendeleev University from Kazakhstan. I'm studying on biotechnology specialization. I'm glad to be here at the International School of Ecology. My expectation for this experience include getting deeper understanding of ecological processes and acquiring practical skills to solve current environmental issues. My goal is to apply the gained knowledge to real projects and contribute to the preservation of our planet. Thank you for the opportunity to participate in this exciting course.
Hello, my name is Diana. I'm from Kazakhstan, and here I graduated medical school, but then I decided that chemistry is more important for me than medicine. And I entered the Mendeleev University of Chemical Technology. And now I study in biotechnology and industrial ecology. And science, my specialty is related to ecology, and I wanted to participate in this school. Thank you.
Hello, my name is Anaya Tsakhanova. I am from in Kazakhstan. I am 21 years old. I studied my bachelor's degree in my hometown of Taraz. My bachelor's diploma I received at Taraz State University, named after Dulatim. If we talk if we talk myself, I work at the Kasphosphate plant. In Kazakhstan, it is one of the best fertilizer production plants. I hope we all learn a lot of new things. Nice to meet everyone.
Who else? Yeah.
Okay, good morning, everyone. So I'm Nisreen, I'm Algerian. So I will try to be precise and concise concerning my background. So my background is quite mixed. So I shifted from social sciences to somehow technical. So first I graduated with BA in language and literature. And then I did specialize in master at the Politecnico di Milano in nuclear safeguards, where we have dealt with international legal instruments and the technical. And currently I'm doing a master in nuclear security in Bulgaria, and I'm Marie Curie, IAEA Marie Curie awardee. And I also had kind of one semester exchange at the RANIPA, Russian Presidential Academy, but due to COVID, it was online. So for my expectations, so I'm trying to get some knowledge and ideas about the ability to balance the cost and security of the waste management. Thank you.
Who missed? Everybody, yeah, except one very shy person. Okay. Thank you all for your presentations. But it's not the final part of of our opening, let's say. We have a small tests for you. It's open question, so there are no correct answers. You should write what you think or what you know. Don't worry, it's will deal nothing with I don't know, certificates or I don't know, judgment about you. And just for us, we will analyze the starting level of the participants, and then at the end it will be the final test after the education, so we can compare if there any progress in knowledges of the participants. So don't be afraid of this test.
As a associate professor, I know how students are very nervous about tests and I don't know examinations, but it's nothing with marks or whatever. So don't worry.
Yeah. So, dear colleagues, we continue. Yeah. Okay.
И на саму презентацию мышки. Обязательно микрофон. И здесь стоять, пожалуйста, если можно.
Могу. Сейчас я вас представлю. Dear colleagues, next lecture, I want to introduce Professor Perminova. She is take care for the ecological issues in our chemistry department. So, Irina, floor is yours. Thank you.
Thank you so much. Thank you so much. Dear colleagues, I was here just half an hour in the morning just to see your faces. And after that, I had to escape for 2 hours. But now we are back together. And what do I want to, first of all, of course, I want to greet you here in our city, at our university. It is very nice to see faces from all over the world. And we are here to speak about ecology. And I heard today the talk by Natalia Tarasova. And it is very interesting because we are coming from the different universities. She is coming from the chemical technology, and I'm coming from this Department of Chemistry of Lomonosov Moscow State University. And we have different versions of what is going on our planet, which is probably nice. I hope you will see it together with me. Okay, the topic of my talk today is natural humic systems and carbon sequestration technologies. And my name is, yes, Irina Perminova, and I represent Laboratory of Natural Humic Systems. And my task today to introduce you to this topic, which I might engage with all my life and love as well. And we will start from the very beginning. So the content of my lecture, Anthropocene, you know already what is it, but we will look at it from the different perspective. And we will speak a little bit about great acceleration, carbon cycling, CO2 pollution as a driver of the climate change. And we will look at the climate change mitigation technologies, carbon sequestration, and I will walk you through the pyrolysis-based utilization of organic waste, which is now state of art of organic waste utilization, and we will speak what is the limitation or why do we need something else. And finally, we will come to my favorite topic. We will come to natural humic systems, and we will speak about why artificial humification and humics-based products instead of pyrolysis and biochar. And I will show you some, from my point of view, exciting examples of using humics-based nature-like technologies. And we will start. Anthropocene, this is the, how to say, enigma for the scientists at the moment. Everybody knows that the Anthropocene is already there. It is already with us. Nobody knows for sure what it is, how it is like. I mean, it is a geological epoch, it is the event, or it is this new era we came in. And just to be sure and to make state of art my knowledge, I was yesterday at the website, which is a working group on Anthropocene, just to find out if there are any news. So what you see there, they agreed about that Anthropocene is already here. They have physically based, what is it, evidence that this new epoch has already started. What do we don't have yet? This is this golden spike. It means what kind of artifacts will be considered as unambiguous proof of that new time what we are living in. But this is geologist issue. What the physicists, chemists, and environmentalists are mostly concerned on of that we see that these humans became this force, geological force. And Vernadsky, he was dreaming that this force will be driven by the reason, but this force is driven by different motivations, and we will see why. This is this great acceleration Natalia was, Tarasova was talking about. We can see that it started exactly in 40s, 50s. This is the beginning of great acceleration, and you can just, with numerous plots, show you population, damming of rivers, transport, so rise in motor vehicles, telephones, international tourism, McDonald's, restaurants, everything is booming up. For me, it was very interesting version. She was asking you why. Do you know why? Epidemia. She was telling antibiotics, yeah, or whatever. What do you think? Do you have different versions? No, really don't. She was saying something about this was a time after the war and all this kind of stuff. Yeah? Okay, let's look at that. What is driving our world? It is definitely, I know, love is great, but it is money. And look at this. You can see that in 1944, what happened in this world when the war was still fought? We got, in 1944, it was Bretton Woods Conference. This Bretton Woods Conference was about future economy of the post-war civilization. And the American economists, they're thinking hard, and by the time of this end of war, 2/3 of the gold from the whole world accumulated in the United States of America. So they calculated that they can actually offer the other countries that $1, it was exactly enough gold in the country to make this direct change between 1 troy ounce, it means 33 grams, and $35. So literally $1, 1 gram of gold. And the countries which, and in this case, this is the base for handle, as you understand. If you accept the rule that $1 is 1 gram of gold, you can convert all your currency inside of the country in dollars and back. It makes much, much easier for what? For trade. You can start trading as crazy. This was such an amazing, because this is a move of the capital. You make investments, you know exactly what to expect. And what happened in our world, we made this very capital, which was laying in gold. It was pretty not mobile, but we made via money, via US dollars, by binding it, we made money moving. And this was the case until when? Because it was at the beginning very fair deal, $1, 1 gram. But in 1971, what happened? In 1971, Henry Kissinger was saying, all of you have already seen that dollar is exactly the goal. And you believe in dollar, and at this very moment, we will disconnect the gold and dollar. And it brought what? It brought incredible inflation. I mean, just like the prices for gold has risen up as crazy. And we see what we see today. And let us look at this response of the planet to this great acceleration. Everything good has bad and vice versa. We live on this planet with good and bad forces fighting with each other. So we can see, yes, CO2, which will be a hero of my today's presentation, has risen up. What do we see? This is the other also so-called greenhouse gases. We see this ozone depletion because Crutzen, who was Paul Crutzen, who coined the term actually Anthropocene. Yeah, he was engaged and he got his Nobel Prize for this very ozone holes. Yeah, he was working on this ozone depletion in atmosphere, and he was so much impressed that the humans, with their activities, could make this ozone going down, that he became a real fighter with the Anthropocene. He wanted bring it more to on the noosphere side, so to make this century of reason. And we see it is the loss in tropical rainforest and the amount of the domesticated land and global biodiversity, which was going down. What we see on this as a result of it, we can see this very planetary boundaries, which we have already far beyond many of them, because this has been agreed by the scientists, which are the thresholds the planet should not go beyond. And we see we are beyond in climate change. I mean, just like with the temperature, and you know that the most sensible, vulnerable areas, this is this Arctic. And today, during your lecture, my student was giving her lecture. She was saying, yeah, Russia has 65% of her land occupied by permafrost. And we are very much concerned about this very climate change issues, because really, world is changing so rapidly. And what Natalia Tarasova wanted to bring to your attention, that we are already here. So we are at this very curve of collapse, because our civilization is not going to stop. And all pictures you look at, they are not so much, how to say, cheerful. Here is carbon cycling, and the major driving force, of course, this is this very CO2. And you know that CO2 is mobile. What do we do actually? Why this CO2 is so dangerous? It is natural, as we say. What is bad in CO2? Because it was laying here in geosphere, yeah, in form of coal. Because everything in our planet is connected into the cycles, and carbon cycling means what do we do with what do we do today? We take these very reserves on conservative coal, we take it carbon, take it out of extract it out of these very reserves, and we introduce it into very labile pool of atmospheric labile CO2. And this is why we have such a huge response to an increase of this CO2. You can see it is 870 gigatons. And the whole land biomass, for example, has a value of 650 gigaton. And in soils, 1,500 gigatons. So they are at pretty high values with you. And of course, a lot of technologies are being set forth trying to mitigate this climate change. And with conventional climate change is what is the main mitigation strategy? Main mitigation strategy, of course, this is with alternative energies. We are using with your renewable energy, which might be wind energy. This is fuel switch and efficiency gains. What do we do by insulation and everything? This is using nuclear power, or we can just go and capture carbon CO2 directly and make this carbon capture and storage utilization. And what is bad in renewable energy? Do you see any bad side in going to renewable energy? Now we are with you in which world? In world of carbon energy. Clear? Solar energy, wind energy, all kinds of great energies, and especially when we speak with you using electrical cars, for example. Yeah, we speak that electrical cars, it is great, is it? Do you have a different opinion?
Renewable energy sources are some problems, like they depend on the atmosphere.
It is very true. Yeah, please.
Once they are expired, then how are we going to handle the waste?
It is absolutely these panels, you are generating new waste. This is one thing, absolutely correct. Another thing, using more land mass in case of solar energy, for example. What do you say?
In nuclear power, do you classify it in
This is conventional mitigation technologies. It is not renewable energies here. This is wind and solar. And this is alternative to carbon. It is not renewable, it is mitigation technology. This is one of the alternatives people still use. And what do you, actually, why it was absolutely right way of thinking. The major, how to say, threat is we are now standing with you. It is so-called energy transfer. Energy transfer, it means absolutely new resources will come to place. Why? Because, for example, one electrical car needs 50 kilograms of nickel, and it needs 8 kilograms of lithium. So it means that we are standing with you, very new players will come to play in this alternative energy world. Nothing bad in this inner side. Of course, we need this diversity, and not only countries which have gas, oil, or whatever should be beneficial countries, but it has huge environmental problems, and those problems, this is for extraction of new and even more metals. These very rare earth metals, for example, yeah, which is a huge at the moment hit, yeah, and we need to think that we are standing just developing also when we bring this renewable energy, electrical cars and everything, new problems will come. So we still have to think holistically about this very earth we are living on, about this very planet. And carbon, now this is this carbon sequestration technology I wanted to speak about. And here we can see that carbon sequestration, in the middle of carbon sequestration technologies nowadays, they put biochar technologies. What is biochar technology? It is you take a plant, which is a natural extractor of CO2, you burn it without oxygen, you get biochar, and you use it. We will look at this because this is one of the central topics for my lecture, and I want to walk through a little bit more. But plus to it, we see here bioenergy carbon capture. We see direct air carbon capture, enhanced terrestrial weathering. And I don't know if you ever heard that the people think about ocean fertilization. How do they want to fertilize the ocean? Do you have any ideas? And what is it for? They want to bring their iron. Ocean is iron deficient. If you bring more iron into ocean, this biomass, this primary biomass will grow immensely. So you will extract huge amount of carbon out of atmosphere, but nobody knows what will happen afterwards. This is why I hear those discussions since 1990, when I moved into the field of climate change, because we were working at the Institute for Global Climate and Ecology. We were responsible for World Ocean Section number 6 at this IPPI Intergovernmental Panel on Climate Change. And what do we see? Biological sequestration. Biological sequestration, what I was telling you about, it is based on this photosynthesis. You work with the plants, And now very big topic. This is the fast growing trees. You must have heard about it. Do you know what kind of trees grow very fast? Bamboo, yeah, eucalyptus. And what else? But what is the major, how to say, paulovnia? There is a tree which it grows 8 meters for 4 years tall. And this is this is also poplars, which is and willow. So those trees are the best fast growing trees. So the idea is we take with you this CO2 and bring it back to the soil. This is all can be shown here again. And the question is to bring it to soil so that it would help, because regular tree is CO2 neutral. It is not CO2 negative. The, how to say, regular or normal cycle, plant, soil, it is carbon neutral, and you need carbon negative. And plus to this, so what do you need? You need actually to bring these plants into the state of humus, thank you, which is characterized by long life in earth. So they need with you carbon pool or carbon, what we just create. We need something on the age of 50 years. So it should live about 50 years in the earth. Only in the soil, in this case, it will be, it will create this very necessary lag phase. To do this, people just were thinking it is good to use compost, biochar, any other amendments to increase this very carbon storage and to make it sit inside of the soil. Your major, how to say, task is not to bring it to degradation. And this is why, which technology came to place? It is this very biochar technology. So what do? You grow your tree, you harvest it, and after that, you apply pyrolysis technology. So by pyrolysis, what is it? It is you are heating it without oxygen. And this brings to the formation of biochar. Here it is this very plant, or this is this equipment to make scheme, technological scheme of this very biochar technology. And what do we see here? Actually, by doing so, you are able to create, or just like to live as a biochar, about 50% of your carbon. So there is no way to get more, because what do? It will be obligatory via oil, hydrogen, or other kind of gases getting out of your incineration. Still, this technology, 50% is considered as big enough, and this is why this biochar technology got a very lot attention. Have you heard before biochar? In this room, you have heard. Do we have somebody who never heard? 50-50. This is good. What a chemical biochar, this is like charcoal. Yeah, so you plus to this, I speak all the time about the trees. The issue is that you can take any kind of organic waste. You can take not only trees, you can theoretically, you can take also the grass, the dry grass, and all the rests from this agriculture and all this kind of stuff, and you will get this. So what do? You take biomass, you conduct this pyrolysis, and you obligatory and inevitably get gaseous products, and you get these bio oil products, because you have liquid and gaseous products of this process. And what do you have afterwards? You get this very biochar, which has a structure, you are not surprised, I think. It is a coal. It is just like a charcoal. It has high surface area. It has hierarchical pores and abundant functional groups. And abundant functional groups depend, of course, on the temperature you are using for the pyrolysis. And there is a lot of chemistry and there is a lot of applications behind just like a search for the uses for biochar, except for just bringing it back to soil. People try to find out how they can use biochar, because it finds applications for catalysis, except for this as sorbents and so on. Here it is, the idea behind is, again, you take your trees and afterwards you conduct this pyrolysis by different temperatures. So you get product with different properties. And major, of course, your task is to enhance pH and micronutrients of soil and introduce here biochar. The regular dosage is 15 tons per hectare. So 15 tons per hectare of biochar gives you this very increased plant biomass, chlorophyll content, and relative water content. And this is a pretty big numbers, as you guess, 15 tons per hectare. And we got just like a whole lectures and everything. All farmers are being taught that biochar is good, you should use it, and biochar is application of biochar technology gives the highest CO2 consumption per hectare in Africa. For example, here are the diagram. And we also have this is a paper in Nature, which showed up in 2016, which was putting biochar at the top of all our management practices for soil to increase, or just like it is absolutely champion in consuming CO2 per hectare, yeah, as you see per year. So this biochar technology was put as this the best technology which ever existed, and with all application diagrams. Here it is the soils which are covered with biochar, and different prescriptions how should you use biochar for different kind of applications. And the whole industries developed behind, because clearly it is very well developed industrial equipment which you can use for these purposes. And also, just like this is a sketch of biochar based economy, so that you can actually using your trees in your forest with having this incineration plant, you can just like, this is like a biorefinery. You can run the whole economy of a village or whatever. And you see there is it was a huge push in a way in the publication, in the amount of publications, because by this, it is since 1984 up to 2021. So recent count, look at that. So for 1,140 papers only from China are getting out, yeah. And here are all the highly industrially developed countries were all on the top of this biochar story. What is your guess why? I mean, just like this is a really interesting story with biochar because it is connected to biomass utilization. And what preceded this very biochar story? Do you remember biofuel? How do you get biofuel? Who knows? How do you do it? Biofuel? No. Biofuel, how do you get? You need to bioethanol. How do you get bioethanol? Pyrolysis? No, you need this hydrolysis using yeast microorganisms. So because this, what is biofuel? You use what? You use your sugars, which are in your biomass, or you use lipids, if you use biodiesel and different kind of living stocks. But what is your major waste? Your major waste is lignin. Your major waste is lignin. Do you know how much lignin is in the tree? Who knows? Lignin, this is aromatic polymer. Cellulose is aliphatic polymer. How much lignin is in the tree? Who knows? 30%. So if you, for example, would like to make your bioethanol out of tree, for example, yeah, what your hydrolytic plant, minimum 30% is absolutely not digestible for your yeast. And but to make it digestible, first you have to treat with acids your wood to hydrolyze, to make it eatable for the organisms, to hydrolyze the polymers, to make this very sugar syrup, glucose-based syrup. And so in the world, there was a huge amount of organic waste and mostly of lignin-containing waste. And nobody knows what to do with lignin. It is very, how to say, very versatile. It is very plentiful because it is biopolymer. 30% of lignin is in this cell wall. And when I was reading in 2004, it was a very, together with biofuel, it was a very big push to make something out of lignin. And I was reading huge international report about lignin use, or just perspective of lignin lignin-based products, written by 3 national laboratories of United States of America, and where it was written, epigraph, you can make from lignin everything, but not money. Because it was written that it was extremely difficult on the short term. They suggested to make fuel gas, but this is actually not a chemistry product. Yeah, it is your burning almost. Yeah, the how to say, middle term goal was to make polymers, biopolymers out of lignin, and absolutely long distance goal was to make low molecular weight aromatic molecules, which is actually the main driving force in lignin, because this is up to date, all aromatic molecules. How do we make it? We take it from, we take oil and aromatize isoprene, and we make our aromatics. So, and all of a sudden, in the middle of all this biochar story, I am speaking about the biochar story with these words because this very group of people who were leading biochar, they were telling everybody that humus does not exist. And it was for us very strange to know that humus does not exist, because I will speak about those substances later. But all of a sudden, in 2020, Marcus Antonietti, who is the director of Max Planck Institute for Colloidal Chemistry, publishes a review, which is called Artificial Humic Acids, Sustainable Materials Against Climate Change. And I know Marcus personally, but after that publication, we got to know each other, because they show on their abstract, they show you collect biomass, you make hydrothermal humification in water, and you create new artificial humic-like products. And you can give new life to these humic-like products. And if you now just search on artificial humification, because in 2022, this artificial humification became IUPAC's merging strategy for the next century. And if you now go for this and look in this Web of Science, you will get huge amount of reviews on this very humification. What did we, for example, this is Chemical Reviews 2023, and it tells you a story that you take biomass feedstocks. Now you ran, this is this very hydrothermal conversion, hydrolytical conversion, and hydrogen conversion and other technologies, and you get practical applications. And what do we mean by this? And why finally everybody started speaking about humification and not about biochar? Why humic acids instead of biochar? And why hydrothermal technologies instead of pyrolysis of biomass? The answer is, while biochar is not humus, and pyrolysis has many disadvantages. And the question is, what is humus? Look at that. Now we are finally by my favorite topic. This is the topic of my life, of my scientific life. And humus in Latin means earth, because it was for the first time extracted from peat soil by German chemist Achard in 1789. And look at that. You have seen it around you. All of you have heard this word before or not? Does anybody hear it for the first time? Do we have these people here? No, for the God's sake. Okay, so this is humus. We understand it intuitively, that this is, as I say, this is life after death. So this is a result of degradation of living organisms, yeah? And this is actually how life makes unlivable planet livable. Living matter is a great thing. And here, what do you see? You can see soils. This is our podzol, for example, where we are with you now. And this is Chernozem soils. You can see it without any biochar. They are pretty black in color. So this is these black rivers containing humics, lakes. And this is permafrost. I was mentioning already, has about 10% organic carbon in it. And ancient organic carbon. And look at this. We also have huge amount of organic deposits, fossil humics and organic waste. This is renewable humics. And these organic deposits, yeah, this is lignite. Instead of using it, what we are doing with it? We are burning it. And lignite has 40% oxygen. Don't burn it, please. I mean, just like it is not useless, but it is not very beneficial. There is a lot of ash, and it is not good for burning, but this is good for extracting humic substances out of it. It is peat, which has 20–40% of humic substances, and sapropel. And we have also organic waste, which is a renewable humic substances, which is compost, oxidized lignin, vermicompost, and so on. And where does it come from? It comes from the global metabolism, which consists of photosynthesis. It is same as in the organism of living person. We have anabolic processes, synthesis. This is photosynthesis on Earth, which is a source of biomass. And we have 60 gigatons per year. This is a newly synthesized organic carbon. And look at that, 20%, 30%, 20 gigatons of this carbon every year undergoes through this humification process and in these humic systems. And if you take this synthetic process and catabolic process, you get metabolic process. So it means photosynthesis and humification produce a cycle, which is global metabolism. And humic systems are actually, this is the ecosystem metabolome or global metabolome. And it is a product of coevolution of living and non-living organic matter. This is how Vernadsky was describing its appearance on this earth. And what do you see? Or what is the difference? How living matter comes, what shapes it does it take? Biomacromolecules produce highly ordered systems of living matter. So this is just like living machines. All of us, we are working against entropy. All of us pumping energy because we want to be stable. We are stable systems when we get this energy. And so work is generally required to produce order out of disorder. And this is how the systems of living matter are being produced. And look now how the systems of non-living matter are being produced. We have degradation process. So this is with DNA, this is the lignin and cellulose, and you get highly disordered matter, which is full or pumped in with entropy. So we get with you highly disordered natural systems. And if you look at these systems as a chemist, you will easily understand why almost 100 years chemists do not want to work with them or didn't want to work with them. Now they want again. Because now we have announced that we are living in the century of complex systems, and not only biological complex systems, but chemical systems. And what do you see here? It is a chemical realization of humic system. This is supramolecular system of oxygenated bioprecursors. You still can recognize in this molecular ensemble residues of lignin, peptides, tannins, or polysaccharides. And but there is, all of them are oxidized, and there is not a single molecule alike. So we have ensemble of incredible complexity and its system properties, chemical diversity, refractory character, and it is a molecular marker actually of ecosystem evolution, which I will not tell you about. Anya Khriptugova will do in her lecture tomorrow. And if you look at it by the eyes of modern high-resolution mass spectrometry technique, you will see that this ensemble, what I was talking to you about, has about, so this is the molecular peaks on this, because this is a high Fourier transform, ion cyclotron resonance chromatogram. We have here about 100,000 stoichiometries. And if you know about isomers, you can easily multiply 100,000 stoichiometries with 100,000 isomers, and you will get 10.10. This will be a chemical space of humic substances, which you see right here in the form of Van Crevelen diagram. And this explains why we did not work with these substances before. Because we didn't know how to measure them, we didn't know how to modify them, and we didn't know how to predict their properties. And if you don't know what to do, if you cannot do all this kind of stuff, you cannot create real applied technologies out of them. But why do we need all this complexity? Just because humic substances do a lot of beautiful things. This was talk by Fritz Friemel, my German Dr. Vater, who was saying that humics might be not nice, but they do beautiful things. And see, they are protecting the cells from living organisms from detoxicants, because they are polyfunctional and they bind the toxicants, and they act as natural stress corrector. And the major topic of my talk today, after the major function of humics, what I will talk today at, they act as the basis for soil fertility. What do you think? Why do they act as the basis for soil fertility? What is their real action? What do they do in soil? Do you know something about soil? Not really. This is not our topic. Okay, in this case, we go further. I will tell you about soil. This is why I will not waste our time. So the main biospheric functions of humic substances are regulatory, accumulative. Regulatory, so they regulate the plant, accumulate the biogenic materials, compounds, physiological, transport, and protecting. So they see that there is a big potential to application of humic substances for developing nature-like materials and technologies. But as I was telling you, this is a substrate of immense complexity, and we have to figure out what to do with it and how to work with it. But before doing that, let us look at soil, because I was putting you a question: what is soil? You think it is just a piece of dirt? No, it is not. It is extremely complex system. It is even more complex than humics per se, because soil has minerals, water, what else? Organic matter, yeah, inorganic is in minerals already. What else? Water, minerals, organics, what else? We come with you. It is not enough. Once again, minerals, water, and organics. What else do you have in soil? Microorganisms and something else. Without it, there is no soil. Nutrients are on the minerals, organics. Silicon also in organics. Plants, no. I even don't know if I have it on the next slide. I didn't know about it. I had to make it. But it has air. There is no soil without air. Look at this soil. This is a fertile layer. And you know, the good fertile soil is airy. Yeah, it should be very fluffy. It cannot lay as a block on your palm. So this is this fertility layer. You can see it is black. And you can see all the other layers. They have different colors. And this black color, and not only color, but the property of fertility, because I also don't know or not, how deep is the fertile layer? How deep is layer of fertility of soil? 15? It is 25, 20, 25, 30. Only in Chernozem, you have 1 meter. But usually I say to my students, you know a spade. Yeah, so this is this very size of the spade. This is the fertility layer of your soil. And usually if you start digging too deep, your mother say, don't do that, because there is no fertile soil deeper. It is all at this top layer soil. So, and here, look at that. You even didn't want to tell me that there is air in soil. Look how much of air is in soil. Soil is composed of 25% air, 25% water, 45% minerals, 5% organic matter, which includes living organisms. So this is your diagram. Of course, it can be plus minus 5%, but it is in general. So what is extremely important, you have almost equal volumes of air and water in soil. It is, I speak about it so distinctively just because this brought us to the new hypothesis of what soil structure is. And good structured soil has soil aggregates. This soil aggregates, it is just like here, bluish space. This is air, and inside should be water. Yeah. And look at this this is this composition of size composition of soil mineral particles. It is again very important to understand that this is a natural hybrid material. Yeah, so we have a few clay, silt, and sand. And sand is between 50 and 2000 microns. And silt is between 2 and 50 microns, and clay, it is under 2 microns. So clay is actually natural nanomaterial, because this is actually all nanomaterial, and it does not depend on the what is it made of. For soil scientists, or just like this is so-called granulometric composition or mechanical composition, all particles lesser than 2 microns, they are clay. All particles bigger than 50 microns, they are sand. And the good soil, which has 40% silt, 40% sand, and 20% clay. So it is in the very middle of this triangle. And depending if you have too much clay, you will have what? Very wetty, humid soil. If you have very much sand, vice versa. And why it is so important? Because fertility of soil is completely almost determined by the soil structure. And what is soil structure is composed of? It is composed of aggregates. And they are different sizes, under 250 50 microns. These micro aggregates, they are so-called agronomically not valuable because they do not produce bigger aggregates. And the meso aggregates between 250 microns and 10 millimeters, they are agronomically valuable aggregates, and macro aggregates which easily fall apart. So our major, how to say, goal is to increase if you want to have fertile soil, you need to increase these very agronomically valuable aggregates, and they should not only have this size, but another condition, they should be water stable. Because you know already, soil has air and soil has water. If your aggregate is not water stable, what will happen? Water comes in and it falls apart. When it just like your rain gets into your soil and all your aggregates are being erupted. Yeah, so they are not livable. And so you need good aggregates. They should swell water as a container and give water back. Swell and give water back. In this case, you will have very good structure of soil, and it will be working. And I have many people who were coming to my lab and they were telling me, could you please make us for us soil amendment, which will make good structure for soil? And I was asking, what property my soil amendment should have? They say, it should create good structure of soil. I say, what is structure of soil? You have these at different sizes. I say, how should I create different sizes? And it was a very long story until we had to figure out what is good amendment. For this, you should look further into the structure of soil aggregate. It is the same rich as an atom, you know, electron is the same rich as an atom, and the same soil aggregate is also, if you come in deeper into it, it is composed of sand, you heard already about it, silt, clay, organic matter. It can be even living organism like a GIF going through this aggregate. And plus to this, it should have water and it should be in touch with air. So this is an extremely complex nano-architected structure. And if you look at it already as a chemist, not as a soil scientist, you will find incredible similarity between these soil aggregates and Pickering emulsions. What is Pickering emulsions? These are the emulsions which are stabilized by the particles. When your stabilizer is not a molecule, it is not a surface active molecule, but it is a surface active particle. And how you can make particle be surface active? Cannot be surface active. It is very modern direction in the material science. Particle is considered exactly as a molecule. One part can be hydrophobic, another hydrophilic, and in this case, it acts. It is like your valency, and you can work with them exactly like with molecules. So let us now imagine what do you have here? So if you, there is a golden rule in colloidal chemistry. If you make emulsion, your disperse phase, so you disperse one phase into the dispersed medium. And to make a stable emulsion, your stabilizer should have the same polarity as your dispersion medium. So if you, for example, disperse oil in water, what kind of stabilizer you should get? Water is hydrophilic or hydrophobic? Hydrophilic. Water likes water. So in this case, you need hydrophilic stabilizer to make emulsion in water. And now you want to disperse water in air. Air is hydrophilic or hydrophobic? Hydrophobic. Try to connect, yeah? And it means the stabilizer, if you want to make emulsion of water in air, your stabilizer should be hydrophobic. And all your particles in soil, your mineral particles, your clays, which can be the size of this stabilizer, they are hydrophilic because they are negatively charged. They are silicates. And this is why to make them hydrophobic, you need these very humic substances. You need these very organic molecules, which are acids, and you have this negatively charged clay, calcium, and organic acid. And you have perfect double, polarity particle. So look at this, how could it look like? Here it is. If you create, here it is a work by Binks, who was publishing in Nature Materials, a paper, phase inversion of particle stabilized materials from foams to dry water. So we are used to use water and oil, so liquid in liquid emulsions, but we know very few or just a little about gas in water or gas in liquid. And if you have gas in liquid emulsion, in this case, if it is air, if you disperse air in water, you will get foam. It is here. If you get disperse water in air, you will get sand. So you will get these particles, which are in each particle, there is a drop of water, but it will behave as a sand. So imagine this might be exactly the case with your soil aggregate. Your soil aggregate, it is water inside, air outside, and mineral is oriented inside with negative charge and outside with its organic molecule. And this is a very, vivid trend in material science today. It is, they are making semi-permeable capsules and containers for food additives, cosmetics, and drug delivery. And nature created already for a very long time Pickering emulsions or dry water out of soil. This is our understanding, and this is how. Look at this kingdom of functions of humic molecules. You can see hydrophobic units, which come from lignins. You can see hydrophilic units, which comes from saccharides. And it gives you a really ability to speak about designer humics. You can modify them, and you can control their state, and you can control their size. And because to make them modify, for example, these minerals, we need something which will go at top of the minerals, for example, silanol groups. And I will show you how binding modified humics onto this glass will make it hydrophobic. Yeah, so this was our concept, that by adding humics into the disturbed soil, we might end up with a restoration of soil fertility. And here it is, again, how we can create this kind of particles or with this kind of structures, stabilizers out of humic by immobilizing humic substances atop of the mineral particles. And this is how it should work in this case. You take this very adhesive derivatives of humic substances, and you put them into soil. They hydrophobize these soil aggregates, and you will get water-stable aggregates out of your not stable aggregates. This was our vision how we can, our way to good property, to good structured soil. And we conducted these experiments, which showed us that we are on the right way. We treated the aggregates, dry aggregates, with this very humics-based adhesives. And we could see that they behave much better as compared to non-treated aggregates. And the reason is because we were just looking at all these chemical mechanisms that they produce very efficient swelling structures, which we need for making this very soil properties work. And this is already a field experiment where you see the Alexander Volikov, who was developing this technique, working in our botanical garden. It still has not very nice soil, which was given to us by the director with an order to make good soil out of it. And this is this accelerated restoration of soils with the use of humics amendments. We could show that we could restore this soil using humic substances which were taken out of coal, amended with silicon, and brought back to earth. And this is just an example how you can make not only soil amendments out of these very versatile materials, you can actually make the whole realm of different materials, because our goal is not only burn organic matter, but our goal is to bring it more into the technology and this everyday need practice to make products out of it. And it is shown all kind of, how to say, modifications. Below is modification with silanols. And we work also a lot with iron, because you need iron for correction of iron chlorosis by plants, for example. And in this case, humic substances can be very useful as this alternative to chelates, because we have synthetic chelates, and they are not always good, because they can be a secondary source of pollution for your soil. And this is why we developed these very iron humates, which are bioavailable for plants, but they are slow release fertilizers. This is what we are working on also currently. And here it is written, how do you test this? How does we test this kind of substances using different plant strategies, like this is wheat and cucumber. And we could show that we can, using humic substances and knowing chemistry also of iron, we can create products with the known properties. Like here it is, our task was to create bioavailable, highly disordered iron hydroxides, and we tested it against highly ordered and synthetic chelate. And we can see that our approach, that humics, I mean, this is also one of the another function in soil, is not only create structure, but also to keep the metals in bioavailable form. And here it is just like we show how they do it. They are not real chelates. They cannot make it as synthetic chelates, but what they can block a growth of the crystals, and they create iron oxides in the soil structure. And these iron oxides are available for plant takeoff. And this is for you just few examples of our late, how to say, achievements and understanding how you can work with it further, because we were working with humic substances, also just trying to create cleanup technologies, because this is our humic bentonite surface washing agent. The task was to clean the oil polluted soil, because you know that humics do a lot of beautiful things. One of them, soil structure. Another, this is with bringing nutrients to plants. And the third one, protecting from the pollution. And here we were using this soil washing agent for just trying to get rid of the diesel fuel pollution. This is far north in our Norilsk area, where we just tested this July this year. We have conducted this field testing of our technology, which showed what does it do. It brings this diesel from soil into water, but again, in the shape of these very Pickering emulsions. And this gives you what? Now your oil is inside, and your oil is inside, and these clay minerals are outside. So this is a versatile mechanism, and you can use it for creating different nature-like technologies. And it was also very interesting for us to work with optics of soil, because this is humic substances. It is a black pigment of soil, and it also has red and yellow pigments. And how usually soil, mask the color. It is because this black pigment is masking the color of iron pigments. Here, for example, treated with it is oxidized, or this is the original, and this is bleached, and you get these very colors getting from the original soil. And here it is the color of hematite, which is the natural pigment, versatile, and lepidocrocite. So look at this picture. This is also how we were taking this hematite covered area, and we tried to show if we can come up with different colors of this hematite colored area, because it is very important for different waste facilities and so on. And for example, here you can just immobilize these humics atop of the stones, and you will get different colors, which is also very, very important when you are handling waste sites. It is not only important not to have this toxic impact, but it is important to make them looking naturally. And this is a sort of like landscape design, a landscaping for these waste facilities, where you can use these natural humic substances, which have very intense color, and give it, it is one more example how you can just change the color. This is a natural color, and this is a color which you bring with using different concentrations and different kind of humics. So these kind of technologies are important for different waste facilities, especially where you get the brightly colored waste, which is also one of the important problems to handle, and there is a nature-like solution to it. And coming back to this very, to what I have started from, and I have started from humics-based products, from lignin. I have started from artificial humification. We think that actually the advantage of this artificial humification is that we can take almost any kind of the organic waste, and we can apply hydrothermal technology, which allows us to conduct this whole process in water. And you will get this water-based products, which you can apply directly to the field. And you can also modify it, because water, we know very well water chemistry. You can also modify to get humic biostimulators, humic meliorants, and many different materials, which I showed you already. And this will hopefully bring us to much more extensive use of humic substances and to much higher values on the future market, because today the major humic materials what we use with is lignite, peat, etc. We use their extraction, and humates are mostly the final product, although I think this is it should be the starting product the chemist should start with. And this is the major fertilizers and biostimulants and remediation agents what they are used for. Now there is a lot of work is being done for functional drinks and for medicine. And I hope that developing chemistry and also developing this artificial humification approach, we are on this exactly eve of exploding stage of humics-based technologies and markets. And to make it, coming back to ecology and to our environmental concerns, I think that development, we are now facing a need to develop basic principle of eco-adaptive chemistry, which is aimed to study molecular mechanisms of adaptation of natural complex systems to the external impact, and so that we could reproduce them in materials, technologies, and processes. So this is very different from green chemistry, because if you know what does green chemistry do, green chemistry mostly reformulate the product, or not the product, the processing way of your product. But the products are almost the same, because the task is not to use these solvents, not to use a lot of energy to come up with different precursors, but you should not come up with different products, because it will change extremely the macroeconomics of your product flow. And this is why, but here you need to introduce new materials, new thinking, learning from nature, and development of advanced artificial humification technologies for combating climate change by sustainable organic waste management. This is also the task which I deliberately give to you. And here it is and take-home messages. This is artificial humification is a new alternative to organic waste utilization. It is a sustainable technology based on natural mechanisms of humification, and this I could not end. Use of humics-based products is also alternative to current developments in biochar technologies. So this is. Thank you all for your attention. And I, of course, want to thank all my lab and all my students who made all this happen, and all my scientific collaborators. And of course, thank you all. So I will be happy to answer your questions, if any, I hope.
Okay, thank you so much. It's so funny how we've forgotten much of our biologies and chemistries. But I want to ask you about those countries you showed us the other time about making producing humus, and also you talked about diesel, something like environmental remediation or something like this. Maybe you could expatiate better for some more knowledge to be understood.
Sorry, once again, your question about use of humics for environmental remediation. Yeah, this is our major actually task, because they are predestined just to be used for cleanup and to be used for all these restoration technologies. But we take the humics mostly at the moment, I have to tell you, we take humics from coal. And this is our major humic cradle, humic resource. And of course, it would be nice to go to this very renewable strategy to make this humics out of organic waste. And these humics, which are made out of organic waste, apply for this very waste site, whatever management. That would be exactly closing the loop. Thank you.
Some more question? No? Okay, thank you very much, Irina.
Thank you so much. Thank you for listening. Thank you. Спасибо всем.
We have a break